All right, AP Physics students, it's time to give away some ideas here about electronic circuits. All right, you have been collecting data on a circuit that looks a lot like this, where you've got a battery that is simply connected to a resistor, and you've been asked to measure the current with an ammeter, measure the voltage with a voltmeter, and track those things as you alter the battery voltage and then later swap resistors and see what that does to the data set. Okay. What I want to say is, first of all, there are some very specific things about this circuit that are true, and then I'm going to tell you what the conclusion should be that you draw from your data. You still have the challenge of defending that statement, and you still have the challenge of looking at the non-idealized elements of the circuit that you can mess around with the FET. Okay, so there's still lots more for you to do. But what's true about this circuit? Well, for this circuit, the current that flows out of the battery that you measure right here will, of course, be equal to the current that flows through the resistor. So that's not surprising to you, and I'm sure that made a lot of sense to you, that whether you measure the current here or maybe measure the current down here, you should get the same value. There's only one loop here, there's only one path for the charges to take, and so one measure of the current in any place in the circuit will be the same as everywhere else. What is also true, and probably pretty obvious to you given our thinking about mechanical analogies, right? Charges pick up energy in a battery, potential energy, and then they deliver that potential energy to circuit elements. And in this case, there's only one element, this resistor here, for the charges to surrender their energy to. So if a coulomb of charge picks up 9 joules here because this is a 9-volt battery, then those 9 joules of potential energy will be delivered to the resistor, with the charges returning to the battery to be re-energized. Having said all that, then for this circuit, the voltage across the resistor will equal the battery voltage. And again, not a big surprise there. One thing to note, though, is that we have introduced this ammeter, and it would be logical to ask, well, isn't there energy lost through that circuit element? And the truth of the matter is that there is a tiny bit of energy lost through the ammeter, but ammeters are designed to measure current without a significant drop in voltage. So our idealized ammeter would be a device that has essentially zero resistance and an ability to measure current. That's probably how the FET is designed, and in practice most ammeters are very close to that, but there is some tiny bit of resistance that they do offer, and so there's usually a little bit of an energy drop across an ammeter, but it's small enough for us to ignore, and it's small enough for us to make these two claims here, and particularly this one, that for this circuit, the battery voltage and the resistor voltage are going to be the same. So I keep saying for this circuit because, of course, there's an infinite number of circuits we could build and kind of explore. But what we're about to uncover is something that is very generalizable, very much universal. Okay, so when we measure the currents and voltages in a circuit like this, we find a relationship between the elements of the circuit, and they follow a particular rule. Okay. And that rule, you might see it expressed as current is equal to voltage over resistance, or voltage is equal to current times resistance. This is known as Ohm's law, and it's true for all individual resistors in any circuit anywhere. Okay, it is the sort of universal rule that one will find for any resistor. Okay, you still have a challenge. Okay, the challenge is that can your data support this? Can you show how your data supports either of these statements. So the same statement when one is just an algebraic equivalent of the other. Okay, but your challenge is to show how your data would support this, and that would be a big step in your summative assignment. Okay. All right, I'm going to end this video with just a quick comment, and that's this. Whatever circuit you have, if you can somehow measure the voltage across a resistor, you can immediately calculate the current using this version of the rule. Or if you can somehow measure the current through a resistor, you can figure out what the voltage must be using that version of the rule. They're again equivalent to one another, and they're true. It's true for any single resistor in any circuit anywhere. Okay, so you're going to apply that to lots of circuit combinations and lots of resistors, and I just wanted you to have that thought and that tool at your disposal. Okay, there'll be another video about the current divider circuit coming up soon.